Welcome once again to yet another session for mathematics. We are starting a little bit behind schedule and I apologize for that. But now we are back on track. So far so good, we have covered a vast amount of topics as far as mathematics is concerned. At this level, we can say for a fact that we are very well prepared towards taking our exams in the coming month. However, to also ensure that we would be adequately ready to do this, we'll be having some set of questions provided to you at a later date where you would attempt to solve them based on all the skills, techniques, as well as areas of expertise that have been covered from the beginning of class till now. Details of these classes will be passed on to you from your community managers. Now, for today, we will round up with yet another intriguing topic. Of course, this again would be our concluding class for the month. The plan is to ensure that subsequent classes will focus more on solutions to past questions so that we can take a vast amount of questions across different topics and then use that as a refresher of our various areas of expertise as well. However, for today, we'll delve right back into the past. In the first class of this mathematics series, we started off with the concept of indices and logarithms. We talked about the fact that these two concepts relate in the extent of the relationship they bear, while the indices talks about the powers and base of operation. The logarithms talk about the base of operation with respect to each number. And then we talked about the relationships that exist within them. For all intents and purposes, we say that if a raised to power b is equal to c, essentially, this just means that b is equal to the log of c to base a. This is the relationship that exists between indices and logarithm, right? So we talk about the logarithm of a number to a particular base. That is simply the power of that particular base of operation itself. So the logarithm of a number to a particular base is the power of that particular base of operation. This is the relationship between indices and logarithms. Now, more importantly, we can talk about a specific field of operation that is very, very important and essential and also stems from this concept. Remember, b is a power that can be any value at all. Any value. Of course, remember that if b is equal to 0, we'll say that that initial value is always 1. If b is any other value that is greater than 0, you can express it as a multiple of that base of operation. And then if b is a negative value, you say that your result is simply going to be a reciprocal. Now, in particular, when b is equal to 1 over 2, what happens? You will now have a raised to the power of 1 over 2, which can also be written as the square root of a. This particular concept leads us to a very, very important and essential concept in mathematics. We tag this concept the concept of surds and surd forms. So today, our study would be on the specific forms of indices known as surds. We will look at the various operations that exist within surds, how to carry out various actions, as well as various simplistic concepts within surds. We will look at rationalization as well as conjugation of values within the surd forms, and then we'll round it off with some basic examples. From then on, we will then pick some basic algebraic fractions, as well as also attempt to solve those algebraic fractions using the concept of indices as well. So today, our topic of operations will be surds. Now, for these surds and surd forms, the very first most important thing you know is that firstly, it is also an indicial form. Because what you call the surd, which is root a, is simply a raised to the power of 1 over 2. So whenever the power is 1 over 2, you say you have yourself the surd form. This surd form is a very, very important area of mathematics. Now, the surd form is not just limited to just having it as root a. The surd form can also be included within a number in itself. What does that mean? For instance, if we have a plus root b, then a plus root b simply refers to the fact that you have your original number, whole number, attached to a surd form. Because it's attached to a surd form by the use of the addition symbol, then together they are referred to as surds or surd forms. So you can say that first and foremost, every surd form consists of a real number part and then a surd part. Every surd form. I might be wondering, why exactly do I say every surd form? What if it's just a surd value that is just there? What will be the real part? This is true because I know that even if I have just the surd form, I can always write the surd form as 0 plus root b. In this case, 0 becomes the real part. Because of this, we say that surds are simply indicial forms that can be written as the addition of a whole number part or a real part plus the surd part. Now, I say a real part because those values don't always have to be whole numbers. You can have them to be fractions. That is a rational number. You can have them to be decimal numbers. You can even have them to be irrational numbers like pi. So long as it's added to a surd part, then the collection becomes a surd form. This is the preliminary information as far as surds are concerned. Now, based on this concept, you would find out that surd forms can either be added together, obviously, or subtracted, or multiplied, or divided. Various basic operations will be carried out. Why? Because those operations can be carried out on the concept of indices. Because of this, those operations will also hold true for surd forms, that is just an indices where the power is 1 over 2. So if you have ever wondered that why exactly can we multiply surd forms, why exactly can we divide those surd forms, know that they are possible, or those operations are possible to be carried out because of the fact that the surd forms are simply indicial forms. Now, let's look at some basic important operations. First off, we know that if I take the surd of A and multiply with the surd of A, my result will simply be A. Right? Whenever you multiply two surd forms such that the inner values are the same, then your result will simply be that inner value. How do I know this? Why? Because this is a raised to power half times a raised to power half. And of course, by the law of indices, when the base is the same, we add the power. This will give us a raised to power 1, which is a. If by extension you want to even use a different law of indices, that is totally fine. If the powers are the same, you can multiply the base, and that will give you a times a, all raised to 1 over 2. And that will be a times a will give us a squared multiplied by 1 over 2, and that will still be a raised to power 1. So essentially, however you decide to apply the law of indices, you will still get a as a result. So this goes to show you that the surds are actually indicial forms in themselves. Also, it also then means that it is also possible to simplify surd forms into their smallest possible forms. What does that mean? If I have the root of base c, it becomes easy for me to express it as the root of b times the root of c. Right? If I have the root of a large number, I can break it down into the square root of the separate smaller numbers. A good example. If I have, for instance, the square root of 32, then it is possible for me to break the square root of 32 into the square root of 16 times 2 and then express it as square root of 16 times square root of 2. And then square root of 16 will give me 4, and then I'll multiply it with square root of 2, and my result will be 4 root 2. A short form. So I'm able to simplify square root of 32 into 4 root 2. These are simplified ways in which we utilize the short form. By the same vein, even if you have a short form of a perfect square, then you can express it as, since the square root of 36, it can be written as the square root of 6 squared, and of course, the square will cancel the square root, and our result will simply be 6. If you're ever wondering that would the square actually cancel the square root, that should not be a problem. Why? Because if you take square root of 6, I can represent that as 1 over 2. And I know that by the law of indices, whenever I have a raised to power b raised to power c is the same thing as a raised to power b times c. So 2 times 1 over 2 gives us 1. And of course, that will still be 6 raised to power 1, which is essentially the same concept. So we'll notice that so far so good, we have been carrying out operations on sorts quite all right. However, what we have been using to carry out these operations have simply been the operations of indices. And that's why it's always essential that before any discussions into the concept of sorts, we must first and foremost discuss the concept of indices and of course logarithms. So now we have seen that yes, we can break down numbers into different parts. It also holds true for division of numbers as well. We take the sort of b divided by c, the same thing as the sort of b divided by the sort of c. That is root b divided by root c. This particular rule makes it very, very important for us to discuss further into the concept of sorts. Now, first and foremost, as far as the ideal mode of writing sorts are concerned, we find out that it is not mathematically tenable to write sort forms in the denominator. Yes, your answers would be correct. However, in terms of the ideal mode of writing mathematics, it is not usually correct to write in the sort forms in the denominator positions. What does that now mean? It means that whenever we have sort forms in the denominator, it becomes very, very important and paramount for us to eliminate the sort from the denominator. This is one of the most important traits as far as mathematics is concerned. Again, this is just a matter of finding ways in which we can beautify and simplify our writings of mathematics. In order to be able to eliminate sort and sort forms in the denominator positions, the concept of rationalization was formed. Now, before we'll be able to delve deeper into the concept of rationalization, we will first and foremost discover and discuss the most important tool we will need for rationalization. And that tool is what we refer to as the conjugate of a sort. So, what exactly do we mean when we say the conjugate of a sort form? Now, the conjugate of a surd form is simply another surd form such that whenever you multiply it with the original, your result is going to be a result without any surd forms. The original is a surd form. The conjugate is also a surd form. However, when you multiply them together, your result is not a surd form, which means your result will not have square root of something inside it at all. So any surd form that allows you multiply with the original such that the result does not contain a surd form is referred to as the conjugate of that surd form. Now, in writing, the conjugate of a surd form A plus root B is another surd form A minus root B such that A plus root B multiplied by A minus root B is equal to A squared minus B. Simple. So the conjugate of A plus root B is that value A minus root B such that when you multiply them together, your result is completely devoid of the surd form. Now you might be wondering what exactly have happened here. You can take this expansion step by step. However, what I have just applied here is what we refer to as the difference of two squares. Now, what does the method of difference of two squares mean? The method of difference of two squares simply says if I have A plus B and then I find its mirror reflection such that the only difference between them is the sign. So since I have plus here, this will have minus. Then if I have two variables in this form, A plus B and then A minus B, the multiplication between them will give me the square of the first variable minus the square of the second variable. This is why we call it the difference of two squares, right? This is a square, this is another square, so we have two of them. The difference between the two of them, that's why we call it the difference of two squares. And if we were to expand it, of course, we would get the same thing. We would have A into A minus B plus B into A minus B. This would expand into A squared minus AB plus BA minus B squared. AB and BA would obviously cancel, and then we'll be left with what? A squared minus B squared. So the difference of two squares is a method that easily makes it possible for you to multiply two variable times. What you just have to do is, as the first term the same thing as the first term in the second bracket, is the second term the same thing the second term in the second bracket, is the only difference between the two brackets the sign? If yes is the answer to all those questions, then all you just have to do is take the first term, square it, minus take the second term, square it, and that will be your final result. In this case, if we take the first term and square it, we'll have A squared minus, if we take the second term and square it, that will be root B squared. And root B squared will simply be the square root and the square will cancel, we'll be left with B. But more importantly, we have ourselves a result that does not contain any surd form. So the conjugate of a surd form is another surd form such that if you multiply them together, your result will simply be a value that does not contain any surd form. And the easiest way to generate the conjugate is whenever you have that surd form, replace the sign in front of the surd form or the sign attached to the surd form by the opposite sign. So if the surd form is attached by plus, change it to minus. If the surd form is attached by minus, change it to plus for the conjugate. That is how to easily identify the conjugate of a surd form. Let's take a host of examples to showcase this, and then we will now apply this concept of conjugates into the rationalization of surds. So far, so good. Do we have any questions at all?
I have a question.
Yes, let me hear your question.
Yes, sir. Please, you just use conjugate of a surd. Can you explain it one more time? The conjugate and the difference. Just one more time, sir, please.
Okay, so let's start from here. Now, this is the difference of two squares. This is a method that holds true for any branch of mathematics.